everyone. My name is John Belsham and I'm the Simulation Product Manager for InterCAD in Australia and New Zealand. This session is being recorded, so any technical difficulties you can email me afterwards and I will give you information about how to view this online afterwards. I've put together a new series of webinars covering the features of our SolidWorks simulation range. Today we'll look at how optimization can help designers and engineers decide which design works best to reduce material costs, reduce weight and shorten the development process time. My colleague Esvand, who is the Technical Simulation Product Manager, will carry out the demonstration today and show two examples of optimization at work, one in metals and the other in plastics. At the end of the presentation I'll wrap up and I'll offer you a special attendance pricing offer for those of you seriously considering the purchase of the product. That's my sales pitch anyway. Next slide please, Esvand. I've added this slide to demonstrate that the traditional serial process and development can be shortened using the SolidWorks parallel process. What we propose is while doing designs we also can simulate those designs at the same time, thus making better business decisions earlier, and lo and behold it shortens the complete development process time. So now to see the optimization at work with Esvand at the helm, so I'll just pass over my headset to Esvand. Thank you.
All right, good afternoon everybody. I'm Sven and I'm Technical Production Manager here. Today we will go through the practical example, two practical examples of design study and optimization. One is on the metal parts and the other on the plastic. Before we starting, let's go and have a review about design study definition. Design study is performing several studies for different input data, which we call them design variables, and review the result as a function of design variables. So basically, any load, any geometry or material property in terms of the magnitude, direction, dimensions, adding feature or removing feature, and the constant and the property curves could be picked up as the variable. And during the design study and optimization process, we can then get a review of our output, which could be variation of stress, this maximum or minimum value, displacement over the different scenarios we have created, and also we can see the deformation over the specific components and its variation through our, let's say, variables. With that introduction, we're going to have a definition of optimization. Finding the best design by changing a geometry or a dimension is the ultimate goal of optimization. So we have an objective to find the best design. We have design variables, which could be our, let's say, geometry and dimensions. And we have our constraint, which are the set of conditions that the optimum design must satisfy. But one thing beforehand, we have to have a base study, for example, an static study or a frequency study or a buckling or a thermal study, to get the base result exported to an optimization process and find the best design. Let's go and have a better overview about each parameters. First is about the goals. The goals define the achievement of optimization process. For example, we're aiming to minimize volume or mass in assembly on a part. Or, for example, we have maximize the buckling load factor or minimize or maximize the response, the resonance frequency of our design. Variables, they are changeable dimension of the model. We can simply pick up any dimension as a design variable. We can pick up any values we putting in our material property as a design variable. But one very important note here, we need to make sure that the design variable do not contradict with any other relation specified in the model. As you can see in the picture, the diameter of the hole and make it bigger and bigger at some, let's say, the case scenario may come with the result of overlapping these two holes, and this is not what we desire. So the selection and the range should be a smart selection. And the other parameter is constraint, the condition that we have to satisfy. For example, it could be elemental or nodal stress, strain, or displacement. If you are in a buckling study, it could be a buckling load factor. In a frequency study, it could be a resonant frequency, or in thermal study, it could be a temperature gradient, or heat flux over the nodes, lines, faces, or the whole volume. Now let's say explain and more explore about the practical example we will have today. We have a press frame design, as you can see in this figure, with the dimension as you can see on it. We aim to first test if our design is satisfying our condition, and second, how we can optimize it. Therefore, our variables are height of the side plate, where currently is 100, but we will go through 50 millimeter up to this nominal value. Length of the back plate varied from 150 millimeter to 375, and cut off legs, where we simply getting it vary between 100 millimeter to 250 millimeter. Our constraint, the condition that we have to satisfy is, first, the maximum stress is less than 100 megapascal, therefore we require a static study. Maximum deformation is less than 1 millimeter. That is the second achievement of our static study, and small natural frequency is more than 80 hertz. So that requires a frequency study. All right, so we might come with a suggestion, as you can see in the picture, and we simply pick up and the software will tell us what is the optimum one. All right, now with that introduction, let's go to the case study and have a look. Here is the design, as you can see, the press frame. If we quickly review the model, we have the top plate, side plates, and we have the back plate. All dimension is, as you can see, its own original values. Now what I have to do, as you know, I go new study and create an static study. Well, I did here. You can see the material for all the parts are plain carbon steel. Have a quick review. You can see it's a linear isotropic material with all the constants of the material is here. Second is how we fix it. We decide that the legs surface are fully fixed, no translation or rotation. And we applied 2250 Newton on that face. All right. Do the meshing and run the study. We can simply review the results of the stress. Well, you can see there is nothing permanently damaged on our actual design because the maximum stress is less than the yield strength, and displacements are showing us 0.32 millimeter maximum displacement. Well, original design is simply confirmed with the set of conditions or constraints that we have simply defined. But the question is it the best design? Could it be better? Can we reduce the mass? Can we play with the dimension? And this is the ultimate goal of our design optimization process. In order to create one, what you need is to go to Evaluate tab, Design Study, and click for a new design study. Well, I have created here. And simply, as we said, the procedure requires 3 steps. First, to pick up your variables. How we do that? Simply, the variables needs to be defined as a set of parameters. And if you go again to Evaluate tab, Parameters, and you will have a new communication box. While you are here, you can go click on any dimension you like, and it will add to the list of the parameter, as you can see, with its original value. Since I've done that, I'm getting back to my design study and click here to add variables. It will do the same job. So you will retrieve all of these 3 parameters as you mentioned. You can ask for a range with the step or secret values, and you put the values. Well, as we agreed, we simply said the back height between 50 millimeter and 100. Feet width is 100 to 250, and plate length is between 150 and 375. So the first step variable been defined. Second is our constraints. Therefore, we need to add a sensor, a measurement device for ourselves. If you click on this, you will get a new communication box. Sensor type could be a mass properties, simulation data, dimension, and etc. Well, we need something from the simulation. Then for the data quantity, you can see you have a wide range of selection: stress, strain, displacement, frequency, and anything else you can see here, including factor of safety. Subcategory of stress, for example, is von Mises stress, principal stress, normal stress, or shear. You specify the unit, and you can ask for the measurement, where it could be its maximum value, minimum or average value over the whole model, or a maximum over selected entities. Well, you can easily select any face, any edge, or even any vertex. So you can trace your result and record your specific result of stress or anything else at some specific locations. So this simply means a sensor, a measuring device. Now the feedback from the measuring device is going to be restricted. So I have defined my sensors like stress, displacement, frequency, and second displacement. Well, each of them I've set a condition to them. Stress 1, which is the maximum stress over the whole model, should be less than 100 Newton per millimeter square, where the base result is coming from press static study. Same for the displacement, should be less than 1 millimeter. It is coming from the base press static study. There is another one, which is the frequency, should be between 80 Hertz and 150 Hertz. Well, this result is coming from press frequency study, which I've previously been created to review the natural frequency of our actual part. And the last one is the displacement over that certain age. As you can see, it's highlighted to be less than 5 millimeter, and it requires the press static study. All right. Now, in this case, what else we can do is simply to go to the last step and simply define our goals. By creating a mass sensor with the same procedure, mass property and mass over the whole model, we can ask the optimization study to minimize the mass while it's varying these variables and maintaining these conditions. So simple as that, you are ready to run the optimization. What will be happen? Software will take all the variation and do a lot of iteration, as you can see in a result view. From iteration 1 to iteration 13, based on what you said, it will go and highlight for you what is required and what is out of the range and what is being achieved. Now, through all of this, you can see there is a summary here, the current value, the initial value, and optimal value. And the good thing, by simply clicking on optimal, simply the model is getting updated, and let's review the optimum value. Where initial design was thinking about the back height of 100 millimeter, while the optimum value is 64.23, whatever you can see there, and the other values, well, you can see the mass for the optimum value is now reduced to 59365, which simply requires 20% reduction from our original state. So that simply means by maintaining all our requirements, we achieve a 20% reduction, which is a very great in a mass production or even in a single design. Well, you're saving money and you're saving a lot of effort. So simple as that, you can see you have optimized your model based on your initial thinking and what is the best one. As we said, any let's say parameters in SolidWorks could be picked as the variable. Now, the next stage I would like to show you, you can review your results and graph and make a specific graph. For example, in the first graph, I can show you one important graph here. how the mass is being reduced by changing the plate lengths. So you can see the variation here. Or even next graph, if I show you here, how the stress value is being reduced while the back high has been changed. So any variation if you like, any trend if you like, you can review and simply go right click, define design study historic graph, or define a local trend graph and add more and more here. And the last bit, all of this could be saved as a report. Here it is. Simply by clicking on that one, you will get a new communication box giving you the highlight of your report and any logo, any address, designer name, or anything you would like to add. And when you simply publish, you will get a report look like what I'm showing you here at the moment. So it's going through your model, get the table of contents, extracting the data for example, model information, study properties, units, and all the columns you would like. It will bring it here, get your results, and simply provide the pictures, figures, and everything. And you can always modify this Word document to be specific to your needs and put in your conclusion or assumption or description as you like. All right. So as we promised, we got the 3-stage done. First, variables. Second, constraint. Third, optimization goal. And simply we found that 20% mass reduction simply can be achieved while we maintaining everything. All right. So that is the first study I would like to show you. This is a medal part. Now let's go to the next example. Here is what I have. And let me just show you the model. The initial knob design is look like what you can see in the screen. We have a hole, a cutting hole, and this is where it's getting fixed. What I would like to see if I can make an optimization on the thickness of this plastic part and also optimization on the ribs. So what I have to do is simply create an static study first. Well, you can see this time I've applied a plastic material with all the properties. Well, you have a selection of linear or nonlinear material and define your specific material here. It doesn't really hurt anything. And then simply look at the boundary condition. I have fixed the hole to have no rotation. You can see it here. Also, I do have a fixing condition to that face. It's not going up and down like here. And simply I've applied a 50 Newton meter torque on the side. That is how the part is actually performing. All right. So simply clicking on run, and then we can look at the result very quickly. All right. Again, stress values less than the yielding point. Displacement values showing us about 0.5 millimeter of displacement. And simply now we are about to say what is next, what is the optimum design. Simple as what the procedure is being explained. You can see the rib thickness. You can see in my model update, rib thickness, cut depth, cylindrical height, and cut diameter. Here is being chosen to vary over the range, as you can see it here. All right. What I would like to achieve, what is the mass reduction, and simply I have to meet the criteria of factor of safety. Should be greater than 2. That's the minimum one. So click on run, and I have the result review. So there are so many iterations, up to 25 it's been created. The optimum one, if you look, is here. So it is showing me from 49.80 grams, we come down to 32.81 grams. So that is the 35% reduction on mass. Well, for those who are in this business, in a plastic injection molding business, it's a huge saving. So multiply by the number of the, let's say, product you have per day, it would be a very great achievement. So the procedure is very simple. You can simply follow up as you can as it's been explained through this webinar. More technical information you can email us later on. Now what I would like to do is passing back the presentation to John.
So I'm back. Thanks, Xfan, for a great presentation of our SolidWorks Simulation Professional product, and in particular the optimization feature. Now, you may have so many questions you may do. Please email me at john.belsham@intercad.com.au, and I'll follow up with everybody regarding any questions. So I believe you've seen a very easy and methodical way to reduce material, reduce weight, achieve design and engineering goals, utilizing SolidWorks design software at its core. Okay, so the important bit, I suppose, next is how to purchase. So I'm not a salesman, this is just information. So you can buy SolidWorks, you might have buy SolidWorks Premium CAD product with Simulation Professional as a bundle, or you can upgrade your existing SolidWorks Premium CAD license to include Simulation Professional. If you're on a network, you can just add the Simulation Professional license to your existing network, and it'll all include a year of support, upgrades, enhancements, or the ISS as we call it in InterCAD world. Training is typically 5 days unless you've already done the 3-day simulation training course. If you've done SolidWorks simulation standard training, then you only need to do 2 days for the professional level of the software. So I've said there, please contact your account manager to discuss this in detail, or if you don't know who that is, you can email me again, john.belsham@intercad.com.au.